Hi everyone, today we're going to talk about vector addition. So before we start today, I just want you to think about some of the lessons that you learned last week and see if you can give two examples of vector quantities and two examples of scalar quantities. Okay, pause the video, see if you can come up with something. Extra points if you can come up with something that we haven't talked about yet. All right, so now that you've tried that out, we'll just talk about a couple of things that you could have put here. So vector quantities, you could have put anything to do with, let's say, velocity, displacement, force, weight, lift, drag, momentum. So if you created two examples with anything that has a magnitude and a direction, you are good. Okay, for scalars, different things that could be scalar examples would be speed, distance, time, temperature, volume, area. Maybe some that we haven't talked about yet would be energy, height of a person, or mass. Okay, so if you haven't come up with two examples yet, you can use these as kind of your framework and see if you can come up with two examples and give actual quantities for those things. The important thing to remember here is that vectors have magnitude and direction, whereas scalars have only a magnitude. Okay, so today we're going to talk about adding and subtracting vectors. So when you add two or more vectors, you are finding a single vector, and we call this the resultant. And this has the same effect as the original vectors applied one after the other. We often label the resultant as a single letter, and we just use the vector symbol above that letter to indicate that it's the resultant vector. Okay, so sometimes we call this the resultant vector, or we just shorten it and we say resultant. Okay, so when you're summing two vectors, there's two ways that you can kind of set this up. One of them is called the tip to tail method, and that's when we create a triangle. So if I have two vectors, A and B, I'll place them tip to tail. If I want to do A plus B, I will put the tail of B at the tip of A, and then the resultant vector starts at the tail of A and meets with the tip of B. Okay, so this pink vector that you see here is the resultant of adding A and B. The other method is called tail-to-tail method, or we call this parallelogram method. And this is when we place the two vectors tail to tail, and then we kind of complete the parallelogram that those two vectors form. So you see these dotted lines over here are completing the parallelogram. So this is essentially an equivalent vector to vector B, and this is an equivalent vector to vector A. So we complete the parallelogram, and the vector that starts at the tail of both vectors and meets at the head, or the finished parallelogram over on the right hand side here, is the resultant vector. Okay, so adding opposite vectors. So yesterday, or in our previous lesson, we talked about what opposite vectors are. They are vectors that are equivalent in magnitude but opposite in direction. So when two opposite vectors are added together, the resultant is called the zero vector. And that means that the combined effect of the vectors is actually equal to, well, they actually cancel each other out. Okay, so that results in the zero vector. Okay, and then adding parallel vectors. So it depends on whether those vectors are working together or working in opposite directions. But if you have two vectors acting in the same direction, you're going to essentially just sum their magnitudes, and the resultant vector will be in the same direction as both the vectors. If you have two vectors in opposite directions, So they're parallel but opposite directions. Take the greater magnitude and subtract the smaller magnitude. The resultant will be in the direction of the vector with the bigger magnitude. Okay, and then there's some properties of vector addition. Commutative property basically just says it doesn't matter which order you add vectors in. So I can add vector u first, or I can take vector u first and add vector v, or I can take vector v first and add vector u. The result will be the same. Okay, the associative property says that if I have more than two vectors that I'm adding, the order in which I add those vectors, so the kind of like the order of operations like we would talk about when we're doing like math, usually we want to do brackets first. But in this case, it doesn't really matter if I do u plus v first or v plus u first or u plus w first. I can do any of those additions in any combination that I want, and I'll still get the same resultant. And then the identity property is just with the zero vector. So any vector plus the zero vector is equal to that vector again, which is also equal to the zero vector plus that vector. Okay, so let's apply some of those properties here to our questions below. So essentially, the associative property tells me that I can do this first if I want. And that actually results in the zero vector there. And we know from the identity property that any vector plus the zero vector is just that vector itself. Okay, and then same idea here. We're just going to rearrange a little bit. So I'm going to use the associative property to kind of group things differently here. So we'll do vector p minus p, similar to what we did in the last question. That will give us the zero vector. And we know from our identity property that any vector plus the zero vector is just itself. And then we have two vectors that are opposite to one another. Vector q subtract vector q, or added with the opposite vector, is equal to the zero vector. All right, so that brings us to subtracting vectors. So here are our vectors, a and b. And I'm just going to show you two different ways that you can set this up. So what you can do is, if you want to find the difference of two vectors, you can take those vectors and you can create a triangle by doing a plus the vector that's in the opposite direction of b. So if I were doing a minus b, I'm doing a plus negative b, or in other words, the vector that is in the opposite direction of b. So I'm just going to actually use these vectors themselves and kind of show you guys here. So there's vector a. And I'm just going to flip this guy so that we can create the opposite vector here. So that's vector, the opposite of vector b. And I just need to clean this up a little bit. All right, so I've cleaned that up. This is the opposite of vector b, which is vector negative b. And then the resultant vector is actually just going to go from the tail of A to the tip of B. So that wasn't great, but should match up exactly with the tip of B. And this will be the resultant of A minus B. Our other option is to think of A minus B, where we arrange the vectors A and B, tail to tail, and then the resultant will be the vector that must be added to B to get A. So the idea is this. If the resultant of A minus B, if we kind of rearrange this equation, we have to take the resultant and add B to get A. That's basically what the description is telling us. So we'll take vector A and vector B. And I'm just going to take a second and clean them up. Okay, so we're going to place these tail to tail. And then the resultant is going to be what we must add to B to get to A, as we said. So if we're drawing this, my resultant is going to be added to B. So it's going to be tail to the tip of B, and it will end at A. So this is the resultant of A minus B. Okay, we can see in both of these I use the same vectors, so you can kind of see here that these vectors are equivalent and they're in the same direction. So you use whatever you feel most confident with. Okay, so let's apply what we just talked about here. Suppose you're given vectors A, B, and C as shown below. Using these three vectors, we want to sketch A minus B plus C. So I'm going to work off of A here. Start with that. So as best you can with a ruler, try to make this equivalent in direction and magnitude. Maybe I should angle this a little bit more. Okay, so there's our vector A. And then when I subtract B, I'm actually just going to do the opposite vector of B. So rather than going toward the right, it's going to be going toward the left. That was not great. One more time. Also bad. Okay, good enough. So there's our negative B, and then we're going to add C to it. So we'll get a little C here, and our resultant vector is going to start at the tail of A and end at the tip of C. So that will be our A minus B plus C. All right, so we have a rectangular box and it's telling us that OA is equal to vector A, OC is equal to vector B, and OD is equal to vector C. Express the vectors in terms of A, B, and C. Okay, so here we have the vector BC. And remember, this is the vector that starts at B and ends at C. So it's going in this direction. So if we find an equivalent vector, which is actually this side here, we know if this is a rectangular box, the opposite sides are equal and parallel. BC is actually going in the opposite direction of OA. So this must be equal to vector A, but in the opposite direction. All right, let's look at GF. Okay, so there's GF. GF is actually equivalent to OA down here. So again, it's rectangular. So we can actually just say that GF is equal to vector A. Okay, OB. So this is actually going to be the sum of two vectors. It's going to be the sum of OA and the vector that is equivalent to OC, so AB. So if this is vector A and this is vector B, this must be equal to A plus B. Okay, AC. Okay, so AC, we already have vectors A and B arranged tail to tail. So if we think about what we just talked about here above, When we have two vectors arranged tail to tail, look at what your resultant is and see where the resultant's tail is, like what vector it's attached to, and that's the vector that must be subtracted from the other vector to get the resultant. So if we take a look here, I'm going to look at where the resultant's tail is, and that's with vector A. So we must be doing here vector B minus vector A. Okay, another way that you can think about this is if we talk about AB, which is vector B, plus BC. This is vector negative A. So we must be doing B plus negative A, or in other words, B minus A. BG. It's this vector here. So we're going to need to use vector C. So an equivalent vector to vector C is vector BF. That's also equal to vector C. And then this vector, we actually did this above, vector GF. Oh, I should have put negative A here. Oh no, sorry, I'm good. Vector FG is actually equal to the opposite of vector A. So we did GF and that was equal to A, so FG must be equal to negative A. So here, this must mean that we have C minus A. Okay, OF is our last one here. So you have to kind of imagine that this is starting at the diagonal or the corner that's closest to us and going diagonal to the opposite corner. So we need to get from O to F using some sums of different vectors here. So I'm going to use this one as my first one, OD, and that's vector C. And then I'm going to use DG, which is equivalent to vector B. And then I'm going to use GF, which we know from above is equal to vector A. So OF is actually going to be equal to C plus B plus A. Okay, and because of our properties that we talked about, doesn't actually matter which order we write C plus B plus A, or A plus B plus C, or any other order. Okay, so one important thing to know as we move forward is whenever you're told an angle between two vectors, it's the angle when the vectors are placed in a tail-to-tail formation. So if this question, for example, tells us that vectors A and B have an angle of 60, we'll actually have to arrange those in the tail-to-tail method, and that 60 degrees is the angle at the two tails. We also know that the magnitude of A is 3, and the magnitude of B is 2. Or I'll just put it off to the side here. Okay, determine A plus B. Well, we talked before about completing the parallelogram when we're adding two vectors. And when we complete the parallelogram, it wasn't amazing. But you get the idea. When we complete the parallelogram, the vector that starts at the two tails and ends at the other side of the parallelogram is the resultant. So this will be A plus B. And I also know, because this is a parallelogram, that this is equivalent to vector B. So I know that the length of this is 2, or the magnitude. And one other thing that we know is that if these are parallel, this is kind of like a C formation. So I'm going to take you back a little bit to grade 9 here. In grade 9, we talked about how when we have a C formation and these two guys are parallel, that actually means that the interior angles add to 180. So I know if this is 60 over here, that this guy must be 120. So if I know that this side is 3, length of 3, and this side is a length of 2, and this interior angle is 120, I should be able to use cosine law to find the magnitude of A plus B. And that means that I'm going to do the magnitude of A squared plus the magnitude of B squared. Just going to move this down here a little bit. Oops. Okay, minus 2 times the magnitude of A times the magnitude of B times the cosine of the angle in between. So perhaps we can call this just theta for now. Okay, so let's sub in our magnitudes. This is just going to be 3 squared plus 2 squared minus 2 times 3 times 2 times the cos of 120. Okay, so we'll take a second to calculate this. All right, so we should have got 19. And then if I want to find simply the magnitude of A plus B, I'm going to square root 19. So if we want to leave it in exact form, we'll just leave it as the square root of 19. Or if it asks you to round to a certain number of decimal places, you can round. But I think the exact value would be preferable. So we'll leave it there. All right, so I just want to show you guys how we can simplify vector expressions. So if we have a parallelogram A, B, C, D, and it's formed with the vectors A, B, B, C, C, D, A, D, or whatever order we want to put those in. It can also be D, A, or B, A, or the opposite vectors. We can simplify expressions both geometrically and kind of like algebraically with this statement here. So if I have AB plus BC, we know that AB plus BC is actually equal to the vector that connects those two things. That was a horrible line. There we go. And that's actually the vector AC. So you'll notice here that this is equal to vector AC. And you'll see that we have a common tail of the, or tip of the first vector and tail of the second vector. So if I eliminate that and I just kind of circumvent that, I'll get AC. So we can actually do this without actually having a picture of this parallelogram, but the picture helps us get a better idea as well of exactly what's happening. Okay, so let's look at AD minus CB. So what we talked about before is that negative CB is actually the same as positive BC. So sometimes what I prefer to do is just write this as AD plus BC to start. And we see that BC is actually equivalent to AD. So what we could write this as is either 2BC, I have 2 of the same vector, or I could write it as 2AD. So in other words, I can say this is AD plus AD, or BC plus BC, and then I have 2 lengths of those vectors. So either 2AD or 2BC, because I have 2 of the equivalent vector. Okay, let's take a look at this one here. So the first thing that I usually do in these types of questions is I'll just reverse any negative vectors and I'll make them positive. And then I also like to just rearrange the vectors. If I notice that one vector has a tip and the other one has a tail that's the same letter, I'll try to group those two things together. So if I have BA plus AD plus DC, we see we have something kind of like what we had above. So anytime I have a vector that has a tip and tail that's the same letter, I can actually just create a single vector. This will be the single vector BC if the tips and tails start with the same letter. Okay, we can also see if we do BA plus AD plus DC, the resultant of that is going to be BC. So we can actually see that visibly in our diagram as well. Okay, and then for the last one here, sorry. CB minus AD plus CA minus DB. So let's just start by switching the negative vectors into their opposite vectors. And then if you see any vectors that we can kind of group together here, so CB and BD, and then I also see DA here that we could simplify. So when we look at all the tips and tails that are matching up here, this can be just simplified to the vector CA. And that gives us CA plus CA, and that just means we have two vectors with the magnitude and direction of CA. Okay, last question for today's lesson. And take a look at another application. In an orienteering race, you walk 100 meters due east, and then you walk north 70 degrees east for 60 meters. How far are you from your starting position and at what bearing? Okay, so a lot of times when I do questions in vectors, I'd like to just start out with like a little north, south, east, west line. And we are starting and going due east or toward the east 100 meters. It's also great if you can create a scale for your drawing. So let's say you let every 1 centimeter equal 50 meters. You can draw this 2 centimeters long. This also only really works if you have a protractor as well that you can measure the angle with. So from there, I'm going to draw another little northeast, southwest line. And from there, we're walking north 70 degrees east. So I'm going to measure off of this from the north 70 degrees toward the east for 60 meters. So here's our resultant. And I'm going to label that vector R as resultant. So here's kind of what we know here. If we zoom in a little bit, So if we zoom in a little bit here, I know that this is 70 degrees. And I know because this is exactly east and this is exactly north that this guy in here must be 90 degrees. So that actually gives us the angle measurement here of 160 degrees. Okay, so that's what's going to help us find the magnitude of the resultant. And then I should be able to find this little angle in here. Maybe we'll call that theta. And that will help me determine the bearing here. Okay, so that's what we're going to do. So for the first part, I'm just going to find magnitude of R, and the way that we're going to do this is we're just going to use cosine law because I have two sides and a contained angle. So the magnitude of vector R is equal to the other two sides added and squared minus 2 times the magnitudes of the other two sides times the cosine of the contained angle. So we're going to take a second and calculate that, and then we will square root the answer to get our final answer here. So we should end up getting 24,876, and we're going to leave all the decimals, and we'll just square root that in our calculator there. So you should get 157.72 meters approximately. So this is our magnitude of our vector. It also asks us about the orientation of that vector. So what bearing is it at? So we're going to also find theta here. So now that I have a vector and its opposite side length, or in its opposite angle measurement, I should be able to use sine law to find that. So sine of theta over its opposite side, which is 60, should be equal to the sine of 160 over the length of its opposite side. Okay, and if you want, you can leave like a couple more decimals here, like what you got in your calculator earlier. All right. So you're going to multiply up that 60, and then you're going to take the sine inverse of this fraction here. Okay, so you can take a second and plug that into your calculator. Again, we always want to make sure for these questions now that we are doing this in degree mode, so no radians anymore. And I am getting about 7.476 degrees. Just double check that in our calculator here. Yep. So that's actually this measurement in here, about 7.5 degrees, let's say. I want this measurement here, so potentially let's just call that x. So what I know between the north and the east line is that that's a 90-degree angle. So if I want to find x, I'm just going to simply take 90 degrees and subtract the angle that I got above, and that's going to give me my northeast measurement. So that's going to give us 82.5 degrees. So we'll say that our resultant is 157.72 meters at a bearing of north 82.5 degrees east. If you want, you can also use quadrant bearing, but usually we'll answer in the same bearing that the question is given to us, but either one is acceptable. If you wanted to use true bearing, you would have put a little 0 in front of your 82, just to indicate that that's a true bearing there, and we do that for numbers that are less than 100.